Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about reaction mechanisms. So let us start learning of reaction mechanism from scratch. So kinds of organic reactions. In general, we look at what occurs and try to learn how it happens. So common pattern describe the change like addition reactions. Two molecules combine and forming a single product. Elimination reaction, when molecule is split into two. You can see the ethanol, it gives ethylene and water. Now substitution, parts from two molecule exchange. You can see methane, it gave chloromethane. Now reaction rearrangement reaction. A molecule undergoes changes in the way its atoms are connected. You can see here CH3, CH2, but in product CH3 and CH3. So learning check. What kind of reaction is the transformations shown below? You can check. This is elimination, rearrangement, substitution reactions, and addition reaction. None of this. So you can check it and write the answer in chat box. Now you see what kind of reaction is the transformation shown below. This is an addition reactions. So how organic reaction occurs? Mechanism. In a clock, the hands move, but the mechanism behind the face is what causes the movement. In an organic reaction, we see the transformation that has occurred. The mechanism describes the steps behind the changes, what we can observe. A reaction occurs in defined steps and that lead from reactant to product. So steps in mechanism. We classify the type of steps in a sequence. A step involves either the formations or breaking of the covalent bond. Steps can occur individually or in combination with other steps. When several steps occur at the same time, they are said to be concerted. So types of steps in reaction mechanisms. Bond formations or breaking can be symmetrical or unsymmetrical. Symmetrical means homolytic, unsymmetrical, heterolytic. You can see bond breaking, symmetrical bond breaking radicals, one bonding electrons stay with each other. So unsymmetrical bond breaking polar, two bonding electrons stay with one product. Bond making, symmetrical bond making radicals, one bonding electron is donated by the other reactants. You can see in this example. Unsymmetrical bonds making polar, two bonding electrons are donated by one reactant. So indicating steps in mechanisms. Curve arrow indicates breaking and forming of the bonds. Arrowheads with a half-head fish hook indicate homolytic and homogenic steps called radical processes, and arrowheads with a complete head indicates heterogenetic and heterogenic steps called polar process. Now radical reaction, not as common as polar reactions. Radical react to complete electron octet of valence shell. A radical can break a bond in another molecules and abstract a partner with electrons, giving substitution in the original molecules. A radical can add to an alkene to give a new radical, causing an addition reaction. So unpaired electrons, you can see the radical red and A and B reactants. It gave radical A substitution product and product radicals unpaired electrons. So steps in radical substitution. Three types of steps. Initiations, homolytic formation of two reactive species with unpaired electrons. Example, formation of Cl atom from Cl2 and light. Propagation, reaction with the molecules to generate radicals. Example, reaction of chlorine atom with mechanism to give HCl and CH3 radicals. You can see. So steps in radical substitution, monochlorination of methane. You can see the methane undergo chlorination, it gave chloromethane. So initiation, formation of chloride radicals, propagation, formation of methyl radicals, and formation of chloride radicals. And then termination, You can see the steps in radical substitution is the termination step, which is last step. Chlorine combine to forming Cl2. Chlorine radicals and methyl radical combine, it gives methyl chloride. A methyl radical and methyl radical combine, it gives ethane. So possible termination steps. With excess concentration of Cl2 present, continued reaction is probable with formation of dichloro, trichloro and tetrachloromethane. So learning check. In a radical chain reaction, what would be the best description of the following reactions? You can see this is the propagation, elimination, initiation, termination, substitution. So your answers you should be right in my chat box. So this is the termination. Now radical substitution with greater than one kind of hydrogens. You have here one kind of hydrogens and two different types of hydrogen. So one chloropropane and two chloropropane. One is blue, another is red. So when there is one type of hydrogen, then there is a greater than one option for radical formations and therefore greater one option for monohalogenation product. You can see learning check. In the reaction of Cl2 with 2-methylbutane, how many monochlorinated isomers are produced? 4. Now polar reactions. You know my friend, molecules can contain local unsymmetrical electron distribution due to differences in electronegativities, and this causes a partial negative charge on atoms and a compensating partial positive charge on an adjacent atom. The more electronegative atom has the greater electron density. So elements such as oxygen, fluorine, nitrogen, chlorine more electronegative than carbon. So you can see the chloromethane, the dipole moment direction carbon to chlorine, and methyl lithium, the dipole moment direction from lithium to carbon. So polarity pattern in some common functional group you can see in alcohol, carbon positive charge, O negative, alkene, symmetrical nonpolar, alkyl halide, carbon positive, partially positive, X partially negative, amine partially positive carbon, partially negative nitrogen, carbonyl partially positive carbon, partially negative oxygen, carboxylic acid partially positive carbon, and two partially negative oxygens, carboxylic acid chloride. You can see partially positive carbon, partially negative one oxygen and one chloride, and aldehyde partially positive carbon and oxygen have partially negative charge. So ether, you can see the carbon positive charge, partially positive, oxygen partially negative, thiol partially positive on carbon, partially negative on sulfur, nitrile partially positive on carbon, partially negative on nitrogen, Grignard reagent partially negative on carbon, partially positive on magnesium, alkyl lithium partially negative on carbon, partially positive on lithium, ester partially positive on carbon, and oxygen, two oxygen have partially negative charge. In ketone, partially positive charge on carbon and partially negative charge on oxygen. So polarizability. What is the polarizability? Polarization is a change in electron distribution as a response to change in electronic nature of the surroundings. Polarizability is the tendency to undergo polarization. You know my friend, polar reaction occurs between regions of high electron density and regions of low electron density. You can see the phenomenon of polarizability in this example. Bond inherently polar already can be made more polar by reaction with the acid or bases. You can see carbon positive, partially positive, and oxygen partially negative. It react with acid in forming partially positive on oxygen and partially positive on carbon and negative charge on A. So methanol weakly electron poor carbon and protonated methanol strongly electron poor carbon. So bond not inherently polar can be polarizable as interaction with the solvent or other polar molecules affect the electron distribution. You can see here the sulfur has negative charge 2.58, carbon have partially positive charge 2.55, and hydrogen. So in carbon partially positive charge, iodine minus partially negative charge 2.66 and 2.55. What does it mean? Large atom with loosely held electrons are more polarizable than small atom with few tightly held electrons. So S is more polarizable than oxygen, I is more polarizable than chlorine. So generalized polar reaction. An electrophiles and electron poor excesses combined with a mononucleophile and electron rich species. Electrophile is a Lewis acid, nucleophile is a Lewis base. A combination is indicated with a curved arrow from nucleophile to electrophile. This curved arrow shows that electrons move from B minus to A plus. So electrophiles A plus, electron poor, nucleophile B minus, electron rich. The electrons that move from nucleophile to electrophile and up here in this new bond formations, covalent bond formation. So you can see here some nucleophile electron rich, ammonia, water, hydroxide ion, chloride ion, and some electrophile electron poor. You can see here this is CH3O plus, CH3Br and ketone. So learning check, which of the following is likely to be a nucleophile and which an electrophile? You write it the answer in the chat box. You see electrophile, nucleophile, nucleophile, electrophile. Now another, is BF3 is likely to be a nucleophile or an electrophile? So answer is electrophile. Now which of the following is expected to be the worst nucleophile? The answer is BF3. Now, an examples of polar reaction addition of HBr to ethylene. You can see HBr add to the pi parts of the CC bond. The pi bond is electron rich, allowing it to function as nucleophile. HBr is electron deficient at the hydrogen since Br is much more electronegative, making HBr an electrophiles. You can see ethylene react with hydrogen bromide, it gives bromoethane, and their electron density. So HBr to ethylene, HBr electrophile is attacked by pi electrons of ethylene nucleophile to form a carbocation intermediate and bromide ion. Bromide ion adds to the positive center of the carbocation, which is an electrophile, forming a CBr sigma bond. The result is that ethylene and HBr combine to form bromoethane. All polar reactions occurs by combination of an electron rich site of a nucleophile and electron deficient site of an electrophile. So you can see here the hydrogen atoms on the electrophile HBr is attacked by pi electrons from nucleophilic double bond, forming a new CH bond, and this leaves the other carbon atom with a partially positive charge and vacant p orbital. Simultaneously, two electrons form the HBr bond, move onto the bromine, giving bromide anion. You can see the ethylene and carbocation formation. The bromide ion donate an electron pair to the positively charged carbon atom, forming a CBr bond and yielding the neutral additions product. So you can see here carbon-carbon sigma bond is stronger, less accessible bonding electrons, and carbon-carbon pi bond weaker, more accessible electrons. So learning check, what product would you expect? What product would you expect? You can see the answer. So using curve arrow in polar reaction mechanism. Curve arrow are a way to keep track of change in bonding in polar reactions. The arrow track electron movement. Electrons always move in pairs. Charges change during the reaction. One curve arrow corresponds to one steps in a reaction mechanisms. So rules for using curve arrow. The arrow electrons goes from the nucleophilic reaction site nu or to the electrophilic reaction site zinc E or E plus. You can see here. The nucleophilic site can be neutral or negative. So rules for using curve arrow. The nucleophilic site can be negative or neutral. Negative charge you can see neutral. Neutral you can see the positive charge. So electrophilic site can be positive or negative. Positive charge you can see here, neutral, and neutral negative charge you can see here. So octet rule must be followed. The hydrogen already has two electrons, so when another pairs move in, the two already on have to be leave. So learning check, what is the role of the alkene in the reaction above? You can see electrophilic, nucleophilic, free radical, catalytic, Lewis acid. Answer nucleophile. So add curve arrow to indicate the flow of electrons. This is the answer. Now add curve arrow to indicate the flow of electrons. You can see Now, what carbocation intermediate is consistent with the product form? Propose a mechanism. Add curved arrow to indicate the flow of electrons. You can see detailed description of sequence of steps involved in group from reactant to product. You can see the reactant, intermediate and products. So bond cleavage, you know the heterolytic cleavage, positive charge ion, carbocation, negative charge ion, carbon ion, homolytic cleavage, free radicals. So carbonium ion, planar sp2 hybridized bond angles 120 degree, has 6 electrons, stabilized by resonance or inductive effect or hyperconjugation. Empty unhybridized p orbital, sp2 hybridization of carbon, planar structure of carbon. Now you can see the examples of carbonium ion, benzyl cation, vidyl cation. Stability of carbocation. The resonance effect is always more predominant than the inductive effect is stabilizing an ion. By inductive effect, hyperconjugations, you can see number of hydrogens. The tertiary carbocation is more stable than secondary and so on. Now carbon ion, pyramidal sp3 hybridized bond angles 109.28 degree, has 8 electrons, stabilized by resonance or by inductive effect. sp3 hybrid orbitals containing lone pair of electrons, tetrahedral structure of carbanion. Now stability of carbanion you can see by resonance, by inductive effect, and stability of carbanion, electron donating groups destabilize carbanion while the electron withdrawing group stabilize it. You can see here. Now free radicals. You know my friends, planar or pyramidal has 7 electrons stabilized by resonance or by inductive effect. Order of stability of free radical 3 to 1. An unhybridized orbital you can see containing odd electrons, sp2 hybridized. Now classification of reagent. You know the nucleophilic reagent, nucleophiles, attack the positive end of the polar bond or nucleus loving is known as nucleophile. Generally negative charge or electron rich species are nucleophile. You can see OH minus OCS3 minus cyanide minus I minus CS3 minus COO minus NH2 minus CH3 minus H2O, ammonia, and more examples. Pyridine. All nucleophiles are in general Lewis spaces. Now electrophilic reagents attack a region of high electron density of electron loving is known as electrophile. All positively charged or electron deficient species are electrophile. You can see the examples. So classification of reagent, neutral reagent which contains an electron deficient atom are also electrophile. You look at here zinc chloride, ferric chloride, phosphoryl chloride, thionyl chloride, BF3, SO3, AlCl3. All electrophiles are in general Lewis acid. So carbene, divalent carbon compound. Carbon atom is linked to two adjacent groups by covalent bonding. A carbene is neutral and possesses 2 free electrons and total of 6 electrons, electron deficient. Now carbene. Carbene is of 2 types, singlet carbene and triplet carbene. You can see here hybridized sp2 is V-shaped and hybridized sp is linear shaped. So triplet carbene is more stable than singlet carbene. Now types of organic reaction: substitution, addition, elimination, rearrangement, condensation and isomerization. Now types of organic reaction. First, substitution reaction, replacement of an atom or group by other atoms of group. Nucleophilic substitution, you can see the example. SN1 reaction, unimolecular nucleophilic substitution reaction. So types of organic reaction, SN1 reaction you can see. Now SN2 reaction, this is called bimolecular substitution reaction in one step process. You can see the transition state unstable. Now addition reaction, the reagent often add to carbon-carbon double bond, triple bond, carbon double bond oxygen and carbon triple bond nitrogen bond, and the pi bond is converted into sigma bond. Can be electrophilic addition or nucleophilic addition. You can see here. So elimination reaction, 2 groups on adjacent atoms are lost as a double bond is formed. So we divide the elimination reaction into 3 categories: E1, E1CB and E2 reaction. Now rearrangement, migration of a group takes place with the same molecules. This is one example here, Beckmann rearrangement you can see, and dehydration and rearrangement. Now condensation, 2 molecules of the same or different reactant combine to give a new product with the elimination of simple byproduct like water, ammonia, etc. You can see the example. Isomerization reaction, you can see the examples. So class exercise was select the most stable carbocation among the following. Solution. Which of the following is an addition reaction? Solution. Which of the following is the most effective group in stabilizing a free radical inductive? Solution. Which of the following is not a nucleophile? Solution. Which of the following is the correct order regarding minus I effect of the substituents? Solution. The least stable carbonium ion is? Solution. Arrange the following ions in the decreasing order of stability. This is the solution. Arrange the following radical in order of their decreasing stability. This is the solution. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.